Our final speaker of the morning is Bhargav Bhatt, who will give his last lecture.
Okay, thank you. Okay, right, so yesterday I spoke about the Hodge state spectral sequence, and I tried to give some indications of how you go about constructing it using the pro-étale topology. And the key thing that I finished at the end with was this computation of the pro-étale cohomology of the structure sheaf on a torus. And I sort of will revisit that computation later today. But the theme today is to sort of go in a slightly different direction. So yesterday's talk and the previous talks were about the rational theory. And I want to talk today about the integral theory. So, not this pen. So integral aspects of the Hodge state decomposition. Well, it's not a decomposition anymore, but. Okay, so say, as before, C over QP is a algebraically closed and complete field. And X over C is smooth and proper. So yesterday, I explained what the Hodge state spectral sequence was, and I mentioned that this result of Conrad and Gaber tells us that the spectral sequence actually always degenerates. So yesterday, in particular, you get a numerical consequence, which I want to write down. So the numerical consequence is that the dimensions of the étale cohomology, QP, say, Hn of xQP, is the same as the sum of the dimensions of the Hodge cohomology groups. Just because the spectral sequence degenerates, so you just sum up the dimensions of the terms that show up. And the question I want to address today is sort of what can you say about things like this when you're interested in more integral objects? So, what about integral or mod P analogs? So in order to make sense of this question, you need to make sense of integral structures on both sides. On the left-hand side, I'm doing étale cohomology. Étale cohomology is defined over ZP, so there is an obvious integral analog, namely étale cohomology with ZP coefficients. You can reduce that mod P to get mod P étale cohomology. So there is a good analog of the left-hand side. But for the right-hand side, if you only have something defined over C, there is no obvious integral analog. You might pick an integral model and use that, but if you want to think about differential forms on an integral model, you better make some assumptions on the model. So I'm going to stick to the case of good reduction, which is the one where the differential forms behave best. So let's assume that X over OC is a proper and smooth model for. So it's proper and smooth, and the generic fiber is X. And so it's a proper smooth formal scheme. Right, so we've talked about how if you have a formal scheme, you can take its generic fiber and you get a rigid space. And you can sort of, if you're not so comfortable with formal schemes, you feel free to assume that these are completions of actual schemes. For the proof, I actually really want to work with formal schemes because it makes certain arguments easier. And it's also more general, so yeah. Okay, and then I want to talk about the mod P analog of this equality over here. So let K be the residue field. So it's OC mod the maximal ideal. Okay, so in this situation, there is a mod P analog of this side, which is a étale cohomology with FP coefficients. And here you can talk about just the Hodge cohomology of the special fiber, which is now just a smooth and proper variety over an algebraically closed field of Kirsig P. So it has sort of well-behaved Hodge cohomology groups. And then the theorem I want to discuss is the following. So I guess it has two parts. So the first part is that we always have an inequality. So the inequality says that the dimension over Fp of the étale cohomology in some degree n is less than or equal to the corresponding number on the Hodge side. Script x little k is the special fiber. one more. Okay. You think I should write a little bigger. Can I do it in the next? Fine. It's good to make Peter happy. Is that okay? Okay, so on the right-hand side, we have the dimensions of these Hodge cohomology groups. You sum them up, and the statement is that you always have this inequality. And then the second part is that you can't really do much better than that. So the inequality can be strict. Meaning there are examples where it is strict. In fact, you can already find an example of a surface that's defined over Z2, the two adics, where the numbers are different from each other. And so maybe tomorrow in one of the projects, the students will discuss one of these examples, which is why I thought I should mention this. Okay, so I want to spend some time today explaining where this comes from and what is the connection with the story we were discussing before. I want to just make one remark on previous work. So I guess, yeah, Peter and Matthew and I wrote a paper about this subject recently. And the previous work in the area was done by, well, lots of people, but notably by Caruso and Faltings. And I don't want to write down the precise statement. Roughly what they prove is that if you're defined over a finite extension of QP, say, and the ramification index is small, and the degree of the cohomology is also small, then you get something. So the precise statement is something like the product of the cohomological degree you're looking at times the ramification index has to be less than p minus 1. And then you actually do much better. You actually get an equality. But, okay. Right. So I want to spend some time talking about this theorem. And the inequality is really just a consequence of a finer statement at the level of cohomology theories. It's going to be another one of these cohomology comparison style results. But since we're not looking for an equality, we're looking for an inequality, you have to sort of think about how you might go about finding this at some cohomological level. The easiest way to prove that dimensions of two vector spaces, dimension of one vector space is less than the dimension of another vector space is to find either an injection in one direction or a surjection in the other direction. But actually, there are examples that tell you can't do that. So there's a slightly better version of the statement where there's a mod p squared on the left-hand side, and you work over sort of W2, and that inequality cannot actually be upgraded to a containment of groups. So you're not searching for an injection. And so then you scratch your head, like, how are you going to prove an inequality if you aren't going to actually find maps of groups? But you don't have to look very far. So one of the things one learns when going through Hartshorne's algebraic geometry is that there is a semi-continuity theorem. And the semi-continuity theorem tells you that if you have, for example, a coherent sheaf on some nice variety, the dimension of the fiber at a generic point is always a lower bound for the dimension of the fiber at the special point. And so if you can sort of put these cohomology theories in some nice family in such a way that the Étale cohomology is the generic one and the Hodge cohomology is the special one, you will get some kind of inequality. And this is the strategy of what we're going to do. So we're going to build a family of cohomology theories that interpolates between Étale cohomology and Hodge cohomology. And this family lives over some base, and the base is what I want to talk about next. So the base is already something that has shown up a lot. So it's Fontaine's A and Thring. And I want to, yeah, okay. So let me just recall the definition. So remember, we have this algebraically closed incomplete field C. It is perfectoid, so you can input it into the constructions we've seen. So you start off with the ring of integers. You reduce it mod P. So now you've killed P, but you get a ring which has tons of nilpotents. Frobenius is surjective, but not injective. And then we have this recipe of taking all those nilpotents and building it up into some kind of an extra dimension, which now lives in characteristic P. So it's the inverse limit along Frobenius of OC mod P, which we called OC flat. And so this guy is a valuation ring of rank 1 in characteristic 0. This guy is a valuation ring of rank 1 in characteristic P. And then you somehow take something that sort of maps to both of them, which is the ring of bit vectors of OC flat. And so this is A inf. Okay, so I mean somehow you have a ring of dimension 1 over here, and then you're thinking of the width vectors, which are power series in P over that ring, so you somehow have an extra parameter. So you would expect that A inf would have dimension 2, and this is not quite true, but it's essentially true. So I want to spend a little bit of time explaining what the geometry of this ring looks like for the purposes of proving these cohomology specialization results. And for that, let me just introduce one piece of notation. So choose a compatible system of p power roots of p. So p to the 1 over p to the 1 over p squared, and so on. And this is a p power compatible system of elements of OC. And so you can think of it as an element of OC flat by this presentation that Jared explained for OC flat, where you can take the same inverse limit but not mod out by p, and you get the same answer. And so this is an element of this ring, and therefore you get an element in A inf, which is this Teichmuller. So P underline is a pseudo-uniformizer in OC flat, and this is just the Teichmuller of that pseudo-uniformizer in A inf. And the philosophy somehow here and okay, before I write this down, I want to apologize. What I'm about to write down is total BS, but I think it's very useful BS. So the philosophy is that there's a formula that A inf should look like OC flat tensored with ZP over F1. Okay, so what this suggests is that you should regard each of these objects as, or OC, say. I mean, they're related by tilting, so they're somehow the same. You should regard each of these objects as like a one-dimensional curve living over some base, and you're taking their product to get a two-dimensional object. And so this will, what? FP should be a tau over F1, and I'm doing a completed tensor product. Sorry. I want to think of this as a product of two curves, and so the parameters coming from each of the curves should give me parameters on this product. And so what this sort of suggests is that what could be true at the level of commutative algebra is the following. So A inf should behave like a regular local ring of dimension 2. So something like a power series ring in two variables, and those variables or the coordinates are the ones I just wrote down. So the one that comes from the factor OC is this P underline, or really is Teichmuller if you want an actual element. And the one that comes from ZP is just P. And so these are some of these two orthogonal directions that you're trying to put together. And this is actually, this has some content. So you can ask if certain theorems that are true for regular rings of dimension 2 are also true, regular local rings of dimension 2 are also true over A inf. So for example, one statement that one learns is if you have a power series ring in two variables, say, then vector bundles on the power series ring, which are all just finite free modules, are the same things as vector bundles on the punctured spectrum of the power series ring. So you remove the close point. And so you have this quasi-affine scheme, and the assertion is that every vector bundle in this quasi-affine scheme is actually trivial, and it extends to the whole spectrum. And so the same statement is true over A inf and it's due to Kiran. And so there are lots of results like this which suggest that this is a pretty reasonable thing to say. So I guess this is page 1, 2, 3. But for my purposes, what this means is that it gives me certain divisors on spec A inf that I'm going to be interested in. So we have these specializations, or just maps really, of rings. So you can take A inf, and you can go down to OC flat by just killing P. So that's sort of geometrically, that's one of the fibers of the two projections that you would have if it was a product of two curves. The other projection is given by this map theta, which I didn't say anything about, but lives over here, and we've seen it many times. Theta is over here. And what you do to go from A inf to OC is you kill a generator of the kernel of theta, and you can choose it to be as follows. So you kill P minus P underline. So here you're setting two of the parameters equal to each other. So it looks like the diagonal. It's setting x equal to y inside A2. And then you can do the other one. So you go to the bit vectors of the residue field K by killing P underline. And this is a slight lie. You don't have to kill just P underline, but all of its P power roots, and then you also have to do a completion. But morally, this is what is going on. So this is one of the two fibers, this is the other fiber, and this is the diagonal sitting inside there. And I'm going to need one more specialization, which is not a quotient, but rather a localization, essentially. So A-inf is W of OC flat. OC flat sits inside C flat, which is this fraction field, and bit vectors is a functor. So I get a map to W of C flat. And what this does essentially is that it inverts the new parameter and then completes. So we have these maps, and I want to draw a picture of how these fit together so that I can use it later. So I want to draw a picture of spec A-inf. It's related to what showed up in Kiran's talk, except I really want to emphasize that I'm drawing the spectrum, so the generic point is there. So here's the close point, and I labeled the close point with its residue field, which is K. Here's the generic point, and I don't know what the generic point is called, so generic point. Here are these sort of three divisors, and the generic points of these three divisors are down the middle. And the residue fields are, so the bottom one is C flat, which is the first one over here. The middle one, which is the diagonal, is C, which is the map theta. And then over here, you just have the bit vectors of K with P inverted. And then we have specializations between them, corresponding to the fact that these are divisors on the spectrum. And you also have these maps saying the generic point specializes to all of these guys. And the specializations themselves have labels. So these specializations are quotients of A-inf. And so the quotient you have over here is just W of K. The quotient you have over here is OC. And the quotient you have over here is OC flat. And this specialization also has a name. You're looking at somehow a height 1 point and looking at the local ring at that height 1 point, which is what W of C flat is. So this is a DVR. This is the special point of the DVR, and the generic point maps to here. And then there are lots of other points in the picture, so I'm not drawing those points. They sort of live somewhere here. I'll need one more of them, which is over here, but I'll come back to it later. And there's a Frobenius map in the picture, which is sort of moving things in the vertical direction. So in the picture Kiran was drawing, we didn't have the generic point, and we were throwing away the close point. And then we were staring at this sort of curve in the middle, and maybe even throwing away these fringe points. I want to keep the information of these missing points in this picture. Is it clear to everyone what I'm trying to draw? Are there any questions about the picture? Okay, so I want to fill in this picture once I write down the theorem. So maybe I'll come back to this picture in a couple of minutes. But the idea is roughly that we want to attach a cohomology theory to our formal scheme in such a way that it sort of lives over the entirety of this picture. And then there are these various specializations in the picture, and when you move your cohomology theory to one of these specializations, you will get an existing cohomology theory. And that will give you the relation between Étale and Hodge cohomology that you were looking for. And so here's sort of the more precise version of the theorem that gives the inequalities. So remember, we had this smooth formal scheme, X over OC. It was proper smooth. And then the theorem is that there exists a canonically attached, sorry, Matthew, naturally attached perfect complex which we call R gamma sub A of X of A-inf modules. So it lives over this ring A-inf with the following comparison isomorphisms with existing cohomology theories. So following comparison isomorphisms. So maybe before I write down the comparison isomorphisms, let me just say that a perfect complex over a ring is just something that can be written as a finite complex of finite projective modules. If you're working over a local ring, it just means it's a finite complex of finite free modules, except you only think about it up to quasi-isomorphism. And so the first comparison isomorphism is with ital cohomology. And so the result here is that you take this complex and you base change it to this ring W of C flat. And you get ital cohomology, except you have to extend scalars to the same ring. So remember, W of C flat is over here. So this is not really a specialization. It's more like you localize at a height 1 point. So this is where the ital theory lives, on this divisor over here. Yeah. Okay. The second comparison is with, so let's do Hodge state cohomology. So Hodge state cohomology turns out it sort of lives over here, this Frobenius inverse translate of this point. So phi is moving this point down here to this point corresponding to theta, and Hodge state cohomology lives on this divisor. Sorry, this is kind of small. Okay. And so the precise statement is you said you need a name for this map. It's just the Frobenius translate of the other one, so let's call that map theta tilde. It is theta composed with phi inverse. And then when you specialize along theta tilde, you should be getting something that is Hodge state cohomology, meaning something which is computed by a spectral sequence whose E2 terms look like Hodge state cohomology. So the statement here is that there exists an E2 spectral sequence E2ij, which goes hi of x, omega j of x over OC, somehow the integral object. There's a twist which I'm ignoring, and hi plus j of this specialization. So you pull back this complex along this specialization. So if you have an explicit complex of finite free modules, you just tensor up along this map from A to this divisor over here. And so when you rationalize this, you will get the Hodge state spectral sequence from before. And then finally, there's one more in the picture, which is de Rham cohomology. Well, there's a couple more, but I just want to talk about de Rham. So whenever you have a morphism of algebraic varieties or schemes or anything algebraic, you can talk about its algebraic de Rham complex. You just do algebraic differential forms and the algebraic de Rham differential. And this is a very classical thing. And you can in particular do it for the smooth formal scheme x over OC. So you can do the de Rham complex of x relative to OC. And that is computed by the specialization along theta. So take R gamma sub A of x, and you tensor, so theta upper star, maybe is a better way to say it, is the de Rham cohomology, again, of the law of complexes of x relative to OC. And so when I'm working in the derived category here, and all the pullbacks are derived. And so what this means in practice is that if you're trying to compute the cohomology groups of the tensor product, they will be computed in terms of the cohomology groups of the original complex and their tors against the thing you're tensoring with. So in this case, the tors against OC regarded as a module over A inf, which is a pretty computable object. And so we spread out, let's see, so we have de Rham cohomology over here. And I'm not talking about crystalline cohomology, but it's also in this picture, so it's up here. And so again, for posterity. And so somehow we have this kind of cohomology theory that is living over this two-dimensional base, and there are all these kind of interesting divisors where it agrees with things we already knew about. And this is useful information. So let me explain how you would use this to deduce the numerical inequalities from before. Okay, so how to deduce numerical consequences from this. Okay, so the claim we had earlier was that the dimension of the mod P ital cohomology, Hn of x with Fp coefficients over Fp, is supposed to be a lower bound for the sum of I plus j equals n of the dimension of hi of xk omega j of xk. over K. So this is the first theorem I mentioned. And so to get it from this, you just so the proof is very easy. So consider the perfect complex K, which I'm just going to write as shorthand, or let me call this M just to avoid confusion. Sorry, M is this perfect complex I have, R gamma sub A of x coming out of this theorem. It's a perfect complex over a ring, and therefore it has the property that whenever you have a specialization of points in your ring, the dimension of the ith cohomology group at the generic specialization is a lower bound for the dimension of the ith cohomology group of the special specialization. So this is the standard kind of semi-continuity result for coherent sheaves at the level of perfect complexes. So pure algebra will tell you that the dimension of Hn of M at this specialization over here, C flat, is less than or equal to the dimension at this more special specialization, which is the close point. So and so this is the dimension over C flat, and this is the dimension over K. This is just by semi-continuity. It doesn't use anything about p-adic Hodge theory. It's just an abstract algebra statement. Okay, but now the theorem allows us to actually understand what these things are. So, sorry, it's inequality. These are dimensions. To understand the left-hand side, I'm specializing M to C flat, meaning I'm going to this divisor over here. But the base change along this divisor is étale cohomology. And so the dimension over here is just the dimension of the étale cohomology base change to the close point of W of C flat. And so if you work out what that means, it's just the dimension of Hn of x étale with Fp coefficients. Because I'm just taking the right-hand side over here in this comparison isomorphism and tensoring with C flat. But that's just killing P first on the left-hand side and then moving up from Fp to a bigger field, which doesn't change dimensions. So here's the object we have. And on the other hand, this side, so this is by part 1 of the theorem. And let's see, for this one, I maybe want to use part 3 of the theorem, because it's the easiest to use. So part 3 of the theorem tells me that when I go to the close point, so when I look at this divisor over here, I'm supposed to get de Rham cohomology. And so in particular, when I go to the close point, I get the de Rham cohomology of the special fiber. So implicitly, I'm using over here that de Rham cohomology commutes with base change if you work in some suitably derived sense. So here, you get the dimension over K of the nth de Rham cohomology group of the special fiber. But the way de Rham cohomology is computed is that you have the Hodge to de Rham spectral sequence. So it's computed in terms of Hodge cohomology groups, and there are potentially interesting differentials at the E2 page. But all that means is that what happens at the E infinity page is smaller than what happens at the E2 page. If there is a non-trivial differential, the dimension of the E2 page will be larger than what happens when you turn the page. And so this guy is a lower bound for the dimension of the E2 page, which is just exactly what we wanted. And so that proves this claim over here, and therefore this inequality. And so, I mean, you can see that this is kind of it's a purely algebraic argument given this theorem, and so you can do variants of it where instead of modding out by p, you mod out by p to the n. You try to not compare the mod p reductions, but you try to compare the amount of torsion you have on both sides. And things work out nicely. Yes? This one? Right, so the statement I'm using here is that if I have a perfect complex over a ring, and I have a specialization eta to s in the ring, then if I specialize the perfect complex to eta, I'll get just a complex of vector spaces over the residue field there. And if I look at the dimension of the nth cohomology group there, that's less than or equal to the corresponding thing for the special point. And so you reduce that to the DVR case, or to the valuation ring case at least. And then it's just a statement about finally presented modules over a valuation ring and how their ranks behave when you specialize. Okay, other questions about this deduction? Yes?
On the right-hand side of the spectral sequence, what is inside the
Theta tilde upper star. So theta tilde is this map I defined up here. It's just you compose with phi inverse on A inf, and then you do theta. So it's this kind of phi translate of this point. And so I base change along that, which is a map from A inf to OC. And that's what theta tilde upper star of this complex is. theta inverse of, sorry, where is theta inverse of A? It's R gamma of A, sorry. It's just this complex. It's a property of this complex that I'm recording. Other questions? Okay, so I would like to explain somehow what the idea is. No, not this. This stays here. This goes here. What the strategy is for proving this, and this is where we connect up with the discussion from yesterday. So let's just try something naive and see why it doesn't work. So, okay, so maybe, yeah. So the strategy. Well, before I try something naive, let me say what the strategy is. So you're trying to define a cohomology theory attached to a scheme, meaning you're trying to compute the cohomology groups of something. So it's better to define the something first. So what we'll define is a complex of sheaves on the formal scheme. And then the cohomology we're looking for is just the cohomology of that complex. So it's better to it's easier to prove a local statement than to prove a global statement. So if you can prove a local statement, it's better to do that. So the strategy is to define a complex which we called A omega of X of A inf modules on this formal scheme itself. So on X. And then set this cohomology theory R gamma of A of X to just be the hypercohomology of this complex. And then hopefully these comparison isomorphisms that we have can actually be proved locally on the formal scheme, thereby avoiding some kind of hard global arguments. That's essentially how it works for B and C. For A, it doesn't work that way, but I'll maybe come back to it later. But so let's just try something to see what goes wrong. So a first pass. So the first pass is to exploit what we learned yesterday, which is Peter's theorem that tells us that if you push forward the completed structure sheaf from the pro-Étale side down to something finite type, then it ends up computing Étale cohomology. Now the completed structure sheaf lives in the world of perfectoid objects, so it makes sense to talk about not the completed structure sheaf, but also its variants like A inf of the completed structure sheaf. You do Fontaine's construction on the pro-Étale site. And okay, let me just write something instead of blabbing. So consider the map nu, which we had yesterday, or a variant of the map we had yesterday from X pro-Étale to this formal scheme, math frac X. So what this map is a map of sites, and what it's saying is that given an affine open subset of this formal scheme, when you pass to the generic fiber, you get an affine open subset of, you get an affinoid open in X, and therefore an object of the pro-Étale site of X. So yesterday I was working on the Étale site. This is something somewhat smaller in some ways. It's just the formal scheme. It's the special fiber. So the only affinoids you care about are the ones with good reduction, essentially. Okay. And so we have, so Fontaine's construction of A inf also makes sense for sheaves. So it gives a sheaf, which I'll call A inf X, which is you take this integral structure sheaf we had on the pro-Étale side, which is just the pullback of the integral structure sheaf from the Étale side. This is a sheaf whose completed version at least is locally perfectoid, meaning if you evaluate it on an affinoid perfectoid, you get a perfectoid algebra. And you can make sense of A inf of that just by the same formula. So reduce mod P, perfectify, take the Witt vectors. And that's what I mean over here. So this is a sheaf on the pro-Étale side of X. And maybe if you want to feel comfortable, you can put a hat here. It doesn't matter because the first step of the process is to reduce mod P. So the hat somehow goes away. But this is the sheaf whose cohomology was understood by the primitive comparison theorem, at least after inverting P. So Peter's theorem tells us that the sheaf on the inside has the property that its cohomology is Étale cohomology. And then you're just doing some formal construction to it. So you would expect that the construction somehow goes through the theorem to tell you that you're computing something you're computing the Étale cohomology not with coefficients in QP, but with coefficients in something like A inf. And so that turns out to be the case. So the primitive comparison theorem still works. Yes? Yes? No, it's the formal scheme. So the formal scheme I want to work only with the formal scheme and not with X etal. So the map I had from yesterday factors the map I have today. I'm saying if I have an affine open in the formal scheme, I can regard it as an affinoid open on the generic fiber.
Oh, now I can.
Right, so the primitive comparison theorem, which I tried to explain a little bit about yesterday, if you sort of go through it actually very carefully, it gives you the following statement. So it tells you how to understand the cohomology of this sheaf. It says that so the theorem is, if you try to compute hi of x pro etal with coefficients in this fancy sheaf, there's one of these period sheaves, a nth x. It's hi of x with zp coefficients, and then you just tensor up to a nth. Almost. So this is the kind of integral object we're interested in, the etal cohomology with zp coefficients. This is a sheaf that's sort of built from coherent sheaves on the pro-etal side, and there's a very close connection between them. They're not quite the same, but they're almost the same. So here A is in the sense of almost mathematics, and it's kind of important that the A is there because the hard work is in removing the A. But I'm not going to focus on that in this talk, so you can ignore it if you want. But the upshot of this is that we already have a sheaf on the pro-etal side, which is computing etal cohomology and is related to coherent things. So the naive guess would be you just push forward the sheaf down to the formal scheme and see what happens. So the naive guess is to just setting R gamma A of x to be something like R gamma of the formal scheme with coefficients in the push forward of the sheaf does the job. So remember, I was searching for this complex of sheaves on the formal scheme with the property that its cohomology was related to etal cohomology tensored up to a nth, or some localization of a nth. And this has the property by the primitive comparison theorem. And so this naive guess has the property that sort of verifies property 1 that I wanted of the comparison theorem, so the comparisons with etal cohomology. And so this is the first thing, indeed, you would try. It's the first thing I tried. It doesn't work, but let me try to explain what goes wrong and how it's related to the computation from yesterday. So if this worked, yes? Yes, it will be, well, it's an almost isomorphism over a nth, but then I'm localizing at this divisor where I've killed almost mathematics. So when I go from a nth to W of C flat, almost isomorphisms become isomorphisms. So, yeah. Yeah, so if this works, then it would also, not only does it work for etal cohomology, because that's how I rigged it, but it should also work for the other comparison theorems, like the Hodge-Tate and de Rham. So let's see if it works for the Hodge-Tate one. So if this works, we would have that when you pull it back along theta tilde, this kind of Frobenius twisted version of theta. Well, the way, the upper star, the formal way how this process works, I guess the technical argument I'm using is the projection formula, tells you that you can move the theta tilde inside cohomology. So this will just be R gamma of the same thing, where you do theta tilde at the level of sheaves. But when you tensor A nth x as a sheaf with theta, or theta tilde, you just get OX. So you get OX plus hat. So the process of tensoring from A nth to OC is killing a single element, namely a generator of the kernel of theta. And the generator remains the same if you have a perfectoid algebra over OC. And so that's roughly what goes into here. So if this was supposed to work, then we would have this, and therefore would know well, we would know that there is an integral Hodge-Tate spectral sequence which computes this object. Because that's what property B in the theorem was. I guess I didn't say this. So when I mentioned the theorem, there were these three isomorphisms. There was etal, Hodge-Tate, and de Rham. Etal is true only globally, meaning you need the properness assumptions. But the Hodge state and the de Rham comparisons isomorphisms are true without the properness assumptions. So they're local statements. And so you would also have such a Hodge state spectral sequence computing this object locally. But that observation sort of puts you in good shape because locally you know how to calculate these things. This is essentially what I calculated yesterday. And so I just want to see parts of that calculation and why it does not work. Okay, so let's recall now yesterday's calculation and what the relation to this business is. So yesterday I was trying to calculate the cohomology of OX plus hat on an affinoid torus, on an adic torus. And the way we did this is we covered the adic torus by a perfectoid cover and did the descent spectral sequence for this cover. So you're doing ZP of 1 invariance for the sections you have up here. And so that would tell you how to compute this object as well, not just rationally, but also integrally. So say X is the formal torus. So OC angle brackets, capital T, plus or minus 1. So this is the formal torus. It's a formal scheme over OC. And when you take the generic fiber, you get the adic torus from yesterday. And the perfectoid theory of this comparison theorem I had yesterday, or the vanishing of cohomology of affinoids perfectoids, tells you that HI of X with coefficients in this push forward is just equal to HI continuous of the group ZP of 1 acting on the perfectoid ring attached to the perfectoid cover of this torus. So acting on OC T plus or minus 1 over P infinity. Okay, so yesterday what I was doing was the rational version. There was no plus over here, and this OC was replaced with a C. And now I've not inverted P. But I explained how to do this yesterday. So this guy was decomposing as a completed direct sum. And on the completed direct sum, it was indexed by Z adjoining 1 over P. And on the indices that were pure integers, the differential was 0. And on the other indices, the differential was an isomorphism in the rational case. And so let me just recall what the output is. If you repeat that argument here, you get the direct sum over all I and Z of HI of ZP of 1 acting on OC times T to the I. Again, the same mistake. Which one? Let's do this one for consistency. I think that's what I did yesterday. And then the same thing for the non-integral ones. Okay, but on these guys, the group action is trivial because T is actually defined below you pass to the before you do anything perfectoid. So these guys are just HI of the complex OC times T to the J, 0 differential OC times T to the J, completed direct sum over all I in Z. So again, the differential was in degree J, you multiply by epsilon to the J minus 1, where epsilon was a primitive J through to unity. If J is an integer, epsilon to the J is just 1, and so it does nothing. And if J is not an integer, then you get something interesting. So again, you have J and these rational guys. And let me write it here. So it's HI of OC times T to the J. But the differential here is epsilon to the J minus 1, OC times T to the J. Okay, so this is the part I want to stare at. So this complex looks like it has the right size. It looks like in degree 0, it has a homology which looks like the ring I started off with, which was my coordinate ring of my torus. And the same in degree 1, coming from here, the coordinate ring of my torus. And then yesterday, in the rational case, these guys were contributing nothing to cohomology because this map was isomorphism, because I was working rationally. And rationally, as soon as I have a non-zero map between two one-dimensional vector spaces, it has to be an isomorphism. But this is not true integrally. So integrally, each of these maps is non-zero, but it's also not an isomorphism. It has a non-trivial cokernel. And so this term over here contributes a lot of extra torsion. And so it's proof that this cannot possibly be true, because this side is sort of computing what the Hodge state spectral sequence should be, and then there's a lot of this extra torsion. I think Peter calls this junk torsion. And so what you really have to do is figure out a way to kill all this extra torsion without modifying what's happening on the integral with the good stuff. Okay, actually, can you tell me how much time I have? Great. Perfect, actually. Okay, so sorry, maybe I shouldn't have done that calculation, but I wanted to explain what the problem was with just repeating the naive argument integrally, which is that you get a lot of this extra torsion, which you can't just get rid of by hand. Locally, maybe you say, okay, just ignore the torsion, but that local recipe is not going to patch together to give you a globally well-defined answer. And so what you need is some kind of a systematic way to kill the torsion in a complex. And if you've thought about derived categories before, this is kind of a weird thing to do. But it turns out it can be done. So this is somehow the new construction. So this is the L-eta construction. And this is just a very general construction in homological algebra. So let me say it in that context. So say R is any ring, commutative. And F in R is a non-zero divisor. And what we want to do is we want to take a chain complex of R modules and find a new chain complex of R modules with the property that you killed all the F torsion in the cohomology of the original chain complex, but done nothing else. You don't want to kill the F squared torsion necessarily, but just the F torsion. If you try to kill all the F power torsion, then there is an operation that does this, but it sort of destroys all possible hopes of any finiteness properties. You just want to do something very mild, like send Z mod P to 0, send Z mod P squared to Z mod P, and so on. So here's a construction that actually does the job. So given a chain complex, K bullet, say, of F torsion free modules. You define a new chain complex, which we call eta sub F of K bullet, as follows. So in degree I, it's the set of all elements in the original chain complex in degree I that are divisible by F to the I. And then what you want is not only you want a complex, so you want the differential to satisfy the appropriate property. So d of alpha lives in F to the I plus 1, Ki plus 1. And so if I is positive, this obviously has a meaning. If I is negative, it means you sort of do the obvious thing where you divide. So this is naturally living as a subcomplex of K bullet adjoin 1 over F. So you get a subcomplex. Eta sub F of K bullet sitting inside here. And the miracle is that I wrote down this recipe, and the recipe totally depends on the choice of complex I had, because I just did something with the terms of the complex. But the miracle is somehow that if you compute the homology of what happens, this is just HI of the original complex, but you mod it out by the F torsion, the pure F torsion. And this is very easy to prove, so I recommend doing this as an exercise if you want to understand what's going on here. But what this tells you is that this is something nice and functorial in terms of the homology of K. And so this operation actually passes to the derived setting. So eta sub F passes to the derived category to give you a functor L eta sub F, which goes from D of R to D of R. So this is just saying chain complexes regarded as objects well-defined up to quasi-isomorphism, and produces a new one of the same flavor by sending K bullet to eta sub F of K bullet for a suitable representative. Okay, so I want to do one example of how this works just to demystify what's going on. So let's say R is ZP, and the element F is P. And the complex K you're looking at is just the constant module Z mod P placed in degree 0. And so what this recipe is, and we want to compute L eta of K. L eta sub F of K. So what this recipe is telling us to do is, since we are working in the derived category, we're allowed to replace our module or complex by anything else, quasi-isomorphic to it. So we might as well work with the complex, with the resolution. So you try to apply eta sub F to a resolution of Z mod P. So the resolution of F is multiplication by P on ZP that you should use, where this guy is sitting in degree 0. And that's certainly a resolution of Z mod P, so it's quasi-isomorphic to K. And now it's a complex of P torsion free modules, so you just do this recipe. And what does the recipe tell us to do? It says in degree 0, you do nothing because there's nothing in degree 1. So in degree 0, you just get the same ZP. But in degree 1, you're supposed to look at all elements that are in degree -1, sorry, all elements that are in p to the -1 of this ZP. So there are elements in 1 over p ZP. And their differential has to be in ZP, but that's obviously true because I'm taking an element of 1 over p and multiplying it by p. So I get this complex. But that complex is just an isomorphism. So its homology is 0. And so this computation tells you that L eta takes Z mod p and kills it. And the same reasoning tells you that if you did it with Z mod p squared, for example, you would get a Z mod p. And so in particular, this is a functor between derived categories that is not an exact functor. It's killing Z mod p and Z mod p, but there is a triangle which expresses Z mod p squared as an extension of Z mod p with Z mod p, and it's not killing the middle term. So it's kind of hard to come across non-exact functors between derived categories, but this is one of them. And then once you sort of realize that there is such a construction, the definition of A omega is very simple. So to go back to p-adic Hodge theory and finish up where I started, so let's say X over OC was my smooth formal scheme. You just define A omega of X to be sort of the thing that wasn't working modified slightly. So the thing that wasn't working was our new lower star of this period sheaf. And the reason it wasn't working was that there was a bunch of torsion that was killed by epsilon -1, but wasn't actually 0. And so you just kill that torsion. So, sorry, L eta with respect to this element epsilon -1 of this complex. And that is perfect. So this is the definition, and then you just check that everything works. But I want to say one more thing. So I should say what the definition, what the origins of these definitions are. So L eta was first described in work of August, verifying Mazur's conjecture on Newton lying above Hodge. And so somehow the same construction comes back and helps us in p-adic Hodge theory. Sorry, let me write the subscript larger. This is epsilon underline -1. Epsilon underline was a compatible system of p power roots of 1. Anyways, this is all I wanted to say. Thank you.
Questions? Okay, I guess it was just too clear.
Indeed.
Let's thank Bhargav again.